Saturday, lesson practice number 9. And before I even get to the practice, I want to go over this. So the question was, which of these, so if you're designing a t-shirt, which of these designs is going to give you the smallest design, the second smallest to the biggest design. So I want you to imagine for a second. Let's try all of them out. We did this, but I'm going over, so you may skip this if you want to watch it. Let's pick something. Let's pick something that's 300. So let's pick something that's 350 miles. All right. So I'm gonna pick New York, and like I said, to Washington, to DC. I think it's 350. Might be a little bit more. Anyways, so in real life, the distance between New York to DC is 350 miles, and I want you to represent that in your notebook using these 6 scales. So which of them is going to give you the smallest? So if you were to draw using scale A, how many centimeters would represent 350? If you use scale B, which how many centimeters, and so forth and so forth. So let's try scale A. So if you try scale A, okay, and I'll do it over here. Okay. For scale A, it says 1 centimeter is 7 miles. And then if we were to represent 350 centimeters using that scale, it's miles. We're going to put 350 here, right? We can cross multiply, we get 70x equals 350, divide by 70, divide by 70, x equals 5 centimeters. So in scale A, and I'll write it right here under it, 350 miles would be 5 centimeters. All right. Let me try scale B. Scale B says 3 centimeters, 7 miles. And then, again, centimeters on top, miles at the bottom, and 350 here. Cross multiply, this time we have 70x equals 350 times 3, which is 700, 1050. And divide by 70, divide by 7. Okay, x is going to be, let me just wait a second, x equals 15 centimeters. So if you were to draw the distance between New York to DC using this scale, you would have to use, it would be represented by 15 centimeters. Third one, size C, 1 to 14, 1 centimeter to 14 miles. So 350 miles using this scale would be how many centimeters? So 14x equals 350, divide by 14, divide by 14. 350 divided by 14, it's going to give us 25 centimeters. So this would be 25 centimeters in your notebook. I know. Select again. The next one, 6 to 150, 6 centimeters to 150 miles. Now I'm going to simplify this one, right, before I even, so if I simplify this to an equivalent ratio, let's divide this by 6. If I divide the top by 6, I get 1. Divide the bottom by 6, I get 25. Alright, so the first thing I'm going to do is change that. So instead of saying 6 centimeters to 150 miles, I'm going to change this and say 1 centimeter to 25 miles. And notice that D and EF are going to be exactly the same. So I'm not going to save me some time because I'm not doing it again. So 1 centimeter is 25 miles. So 350 miles would be how many centimeters? Well, 25x equals 350, divide by 25, divide by 25. X equals 14. So we're going to say that this one is 14 centimeters, and this one is also 14 centimeters. We have one more left to do, and that's 2 centimeters to 35. And again, I should have done it I should, and I'll get back to it. So 2 centimeters is 35 miles. I'm going to simplify that. 2 centimeters to 35 miles. And then if I simplify, if I divide by 2, I get 1 centimeter. I divide the bottom by 2, I get 17.5. So this one, 1 centimeter is to 17.5. And that's how I'm going to set up the problem. So 1 centimeter, 17.5 miles, represents 17.5 miles. So 350 miles in that scale would be how many centimeters? Well, 17.5 x equals 350, divide by 17.5, divide by 17.5, x equals 20. So here, it would be 20 centimeters. Let me do one more thing before we start comparing. I'm going to change this guy, because everything is in unit rate, right? We're comparing everything to 1 centimeter, except scale B, it's 3 centimeters. So let me simplify that as well. It's 3 centimeters, 70 miles. So what is 1 centimeter? I'm going to divide that by 3. Divide the bottom by 3. So 70 divided by 3, oh, it's not going to give us a nice number. So it's going to be 23, and I'm going to put it as a fraction, 1/3 miles. So this one is 1 centimeter to 23 and 1/3 miles. Now, let's talk about this. So if I use scale A, using scale A is 5 centimeters. And I'll draw it here. This is 5 centimeters. If I use scale B, right, it's going to be 15 centimeters. If I, oops, sorry, I made it too small. Let me change it. I apologize. So let me change it. So let's do A again. So A would be 5 centimeters. And I'm going to make this 5 centimeters. Okay. If I took a ruler and measured, that would be 5 centimeters. And that would represent New York to the DC in my notebook or in your sketchbook. B, if I use scale B, it'd be 15 centimeters. If I use scale C, it'd be 25 centimeters. If I use scale D, it'd be 14 centimeters. If I use scale E, it'd be 20 centimeters. And scale F is exactly, it's 14 centimeters as well, just the same as scale D. So that part of the distance between New York to DC, you can tell now that depending on the scale you use, it's either represented by a smaller distances in your notebook. So some of them will measure 5, some will measure 15, some measure 25, etc., etc. So order the design from smallest to largest. So if I were to represent New York and DC in my notebook, which scale would give me the smallest design, the smallest representation would be A. This guy would be the smallest one. Would be the largest one would be C. All right, so this would be the smallest design. This would be the largest design. Now, what do we notice? Well, let's look now, okay, at the scale. And then let me erase this. I erase this. I erase this. I erase that. Erase that. And I'm going to erase that. So look at the scale right now. I'm actually going to get rid of erase this. I want you to use a scale. All the scales where we're comparing it to 1 centimeter. So I'm going to get rid of this because it's simplified to 17.5, and this one simplifies to 1 to 25. So the smallest design, the smallest representation of 350 miles happened to be scale A. And notice that in scale A, 1 centimeter represents 70 miles. The largest one, the largest representation of the notebook, had the scale of C. Of 1 centimeter to 14 miles. So it almost has the opposite effect, right? So if your ratio is 1 centimeter to a large number, right, to 70 miles, like A, in your notebook, you actually get the smallest representation. If you have a scale where you're comparing 1 centimeter to the smallest amount of miles, guess what? On your design, it actually turned out that it came out to be the largest measurement in centimeters in your notebook. Okay. Why is that? Well, because in here, every centimeter, we're stacking 70 miles in every centimeter. Every little centimeter, we're putting 70 miles. So obviously, we cover more with less centimeters. Where opposed to this one, look, 1 centimeter. For every centimeter here, how many are we putting in here? For every centimeter, we're only putting 14 in each, whereas here, we're putting 70. So it's going to take more centimeters using scale C, right? Because we're only putting 14 centimeters in each centimeter, 14 miles in each centimeter. So it's going to take more centimeters to represent miles using scale C. Okay, hopefully that helps a little bit. So that was I forget what page that was, 66, okay? And describe your strategy for ordering designs. I would write that you compare the ratios, right? You compare each of the scales. So 1 centimeter to 70 miles. The other one was 1 centimeter to 25 miles. And 1 centimeter to 40 miles. And you compared, because everything was in the unit rate, where everything was compared to 1 unit, you were easily able to compare the number of miles that fit in each centimeter. And the more miles that you fit in each centimeter, the smaller the design will be. Okay. All right, so let's look at what was next. Yeah. So the lesson summary. We can represent a place or object using many different scale drawings. Right? And again, depends on the size of the paper that you have. The bigger the size, you want to use a scale that it has that will give you the bigger design, right? So a scale where the ratio is 1 centimeter to like 14 miles, like we did in the previous example. Here are 2 scale drawings of New Mexico. The first drawing uses a scale of 1, and if you look here, right, every unit in here, every single unit, right, because it doesn't say if it's centimeter, inches, or whatever, they just call it units. So in every unit, we're putting 40 miles in there. And every unit here, we're putting 60 miles inside. We're representing, right, so there's more miles in the same unit in the second example than the first one. So when we represent a large distance for each unit scale, the size of the drawing decreases. This is because it takes fewer units, like I was telling you, to represent the total distance. For example, in the fourth drawing, it takes 3 units to represent 120 miles. And again, each of this is 40, so here's 0, that's 40, plus another one 80, plus another one 120. So that's 120 miles. Whereas the second one, it only took us 2 units, right? Because every unit here was 60, and every unit here represents 40. Okay. Right, so where were your 2 problems? Problem 1, Taylor made a scale model of Earth. So this is his little scale model. The scale maps the scale model to the actual Earth is 1 inch is 1,070 miles. So given to us, right, the information given to us, the scale that's given to us in this case, 1 inch, every 1 inch in his model represents 1,070 miles. If the height of the scale mile is 7.4 inches, so if that's his model, this is 7.4 inches. Obviously, our planet is not 7.4 inches, but so what does that represent in reality? So what's the height of our planet really? Well, using that scale, let's fill in the units on the other side. So miles on top, inches on top, miles at the bottom. We want to find out what 7.4 represents, right? So we're going to find the equivalent ratio of 1 inch and 1,070 miles in terms of 7.4 inches. So you can cross multiply. I mean, there's, again, whichever one you feel comfortable. So if you look at this, how did the 1 become 7.4? You say, hey, I multiplied that by 7.4. We can repeat the process and multiply the bottom by 7.4. So 1,070 times 7.4 gives us 7,980 miles. So in real life, the height of this, of our planet from here, the bottom to the top, is 7,980 miles. If you wanted to solve the proportion, right, we could have done what we have done in class. So this is x, cross multiplied, x times 1, right? We multiply these two. And then 1,070 times 7.4 is 7,918 miles. Okay. Here, Leonardo da Vinci famous painting, the Mona Lisa, measures 21 by 30 inches. So that's in real life. 21 inches going left and right, and height is 30 inches. Create a scale drawing of the outline of the Mona Lisa where 1 unit represents 3 inches. So I want to draw this Mona Lisa, right? I'm going to take Mona Lisa and put it over here using this scale right here. Okay, so using that scale, well, let me work that here. It says that 1 unit is 3 inches. We can now figure this one out. What's 30 inches? How am I going to represent 30 inches? How many units will it take to represent 30 inches? Well, unit on top, inches at the bottom. I put 30 inches at the bottom. X over here, cross multiply, we get 3x equals 30. Divide by 3, divide by 3, x equals 10. So it's going to take 10 units, and I'm going to do this. Here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There. These 10 units represent 30 inches because this is 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. There. Okay, so it's 10 units. The 10 units represents 30 inches. What about the 21? Well, I'm going to set up another proportion. Or if you don't want to set up a proportion, you can count by 3, right? So look, the first one, change colors here. Right, so 3, 6, 9, 12, 15, 18, 21. 1, 2, 3, 4, 5, 6, 7. And there, this is 7 units. So I'll just close this up. So there's our representation of the dimensions of this Mona Lisa using this scale, where 1 unit is 3 inches. Right? What about the one on the right? The one on the right says, hey, 2 units represents 5 inches. Now you might say, hey, but I want to simplify this. If you simplify this, find the equivalent ratio in terms of 1 unit. Well, let's see. We can go 2 divided by 2, which is 1. So if I divide it by 2 at the bottom, we get 2.5 inches. So every unit represents 2.5 inches. Now, notice that that's a little bit of a pain, right? Because if you go 1 unit, it's supposed to be 2.5 inches. So, right, if you're comfortable counting by 2.5, that's completely fine as well. All right. So if you take a look at 30 inches, let's do the proportion. Let me just do the proportion here, and I'm going to keep the initial scale. So 2 units, 5 inches. We want to know how many units we're going to use to represent 30 inches. Cross multiply, we get 5x. 2 times 30 is 60. Divide both sides by 5. X equals 12. So we need 12 units. So let's count 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Hopefully, that helps putting my glasses on. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, that's 12 units. Could you have used the other scale? 1 unit is 2.5 inches. You could have. Same thing. Let's do 21. With 21, so 2 units is 5 inches. That's the scale given to us. And I want to know what 21 inches. How many units will I use to represent 21 units? So x units, cross multiply, we get 5x. 21 times 2 is 42. Divide by 5, divide by 5. 5 divided by 5 is just 1, times x is just x, and 42 divided by 5 is going to give me, let's see, x equals 8.4. So you're going to have to count 8 full squares. 1, change colors. 1, 2, 3, 4, 5, 6, 7, 8, and then 0.4, so a little bit less right there. All right, a little bit less. Right, it's not going to be half a square, but a little bit less in there. So using that scale, here is 12 units. And at the bottom, it's 8.4 units. Okay? Imagine a new scale, oh boy, of the Mona Lisa where 3 units represents 1 inch. Is your drawing going to be larger or small? Well, let's write this down. So it says what happens when you have 3 units with 1 inch. Do you think the drawing is going to be smaller or equal to the ones that we just did? Well, it says, so remember that it's 21 and this was 30 inches, right? Well, we just do the proportion and figure it out. So 3 units is 1 inch. So units on top, inches at the bottom. And we want to know, we're going to try 30. Because 30 inches would be how many units? Well, x. We go cross multiply x, 3 times 30, 90 units. Oh my god. So this, so if you, so let's count from here. So that's 0, right? So we can have to count 1, 2, 3, 3 units, that's 1 inch. I'll write 1. 1, 2, 3, that's 2 inches. Sorry, we're going the wrong way. Let's start at the bottom here. So starting at the bottom. 1, 2, 3, 1 unit. 1 inch. 1, 2, 3, 2 inches. So that's 1 inch, 2 inches. 1, 2, 3, 3 inches. Notice that we have a long way to go, and I'll just go a few more. 1, 2, 3, 4 inches. 1, 2, 3, 5 inches. We have to go 30 inches. So this is going to be a much larger design. All right. Because it takes more units to represent a single inch. A single inch. Okay. Yeah, we're not going to draw that out. 5. Floor plan. So let me floor plan of a restaurant. So let me draw the restaurant. It's a scale. Let me write that scale first. It's 1 inch. It's 12 feet. So every inch on your picture is 12 feet in real life. The floor plan shows an area of the area of the square area of the restaurant 60 square inches. So here is our floor plan, and I'm going to write 60 square inches. Okay, Hong says the actual area of the restaurant is 720 feet square. Okay, is Hong correct? Explain your thinking. But the actual area of the restaurant, let me try it out. Sorry, I don't make the same. So this is the real restaurant right here. 720 square feet. Is he correct? Explain your thinking. Just a moment. Oops, sorry. One second, guys. Well, for this one, we can try and play. So in order for area, so let's try one here. Let's make this 6. In order for that to be 60 square feet, this could be a 6 and this could be a 10, right? Because 6 times 10 is 60. Now, that was true, right? It would mean that in real life, something is 6 inches. It would be, and we want to know how many feet that was. So let's cross multiply, and we multiply by 12, so we get x equals 72. So this guy here would be 72. All right, so this one, it says the value of the expression 15 times 0.75 is less than 15 or greater than 15. Well, let me put it this way. Multiply 15 times 1, you get 15. Multiply 15 times 1, times 1.1. Okay, I'm going to increase it just by a little bit. Okay, multiply 15 times 1.1, you get 16.5. And you can play with a few numbers here. So 15 times 1.0001. 15 times 1.0001. You get 15.0015. So notice that, and we talked about this, if I multiply 15 by 1, I get the same number. But if I multiply 15 by anything greater than 1, it's going to be greater than 15. Now what happens if I multiply 15 times, and let's pick a small, a number very close to 1, 0.99. If I multiply 15 times 0.99, do you think I'm going to get a number equal to 15? Or less than 15? Well, because times 1 is 15, and 0.99 is less than 1, so can't it be equal to 15? Well, if you multiply now, you would get 14.85. So remember when we talked about, we were talking about scale factors. If you multiply by anything that is greater than 1, it will increase, right? If it's less than 1, your scale factor will decrease, and if it's equal to 1, it will be equal or the same. So 15 times 0.75, and where does 15.075 fall into? Well, 0.75 is less than 1, so your answer is going to be less than 15. This one, the value of the expression 15 times 1.3, well, if it was equal to 1, it'd be 15, but since it's greater than 1, it's going to be greater than 15. Okay. Determine the missing value in each equation. 32 times something equals 4. Okay, so how can you do this? Well, you can use fact families, the ones you learned in 3rd grade. You can set up an equation if you like, right? So let's take a look at this. 32 times something equals 4. Well, 4 times something equals 32. Now, so let's take a look at these ones. There are different ways to solve this. Let's see. 32 times something equals 4. So 32 times something equals 4. Well, I want to know what this x is. So 32 times a number that I don't know represents by x equals 4. We could solve it as an equation, right? Which means we would have to divide this side by 32, right? And divide this side by 32. 32 divided by 32 is 1. 1 times x is x. 4 over 32 simplifies to 1 over 8. Number 9, I mean, think about this one again. It's very similar. 24 times a number I don't know equals 3. Right? So we can divide this by 24, divide this by 24. That equals 1. X, 3 over 24 is the same thing as 1 over 8 again. Ooh. 16 times something equals 2. We can divide by 16, divide by 16. X equals 2 over 16, 1 over 8. It's the same answer. And then 8 times something equals 1. Well, there's a word for this, right? 8 times this, whatever this guy is whatever this guy is equal to 1. What's the relationship between this number and the number we currently don't know? Let's divide this by 8. Divide this by 8. 8 divided by 8 is 1. And x equals 1 over 8. So 8 and 1 over 8 are called, remember, reciprocal. Okay. We could have done it differently. Well, what if we think about it this way? 32 divided by a number equals 4. Well, we all know that, right? 32 divided by 8 equals 4. But this one says 32 times something equals 4. If you remember division, division is the same thing as multiplying by the reciprocal, right? So it's 32, and division can be represented as multiplied by the reciprocal of this number. 32 times reciprocal of 8 is 1 over 8 equals 4. The 32, what's 1/8 of 32? 4. It works. Look at this one. 24 divided by a number I don't know equals 3. And since we know that division can be represented by multiplying it by the reciprocal, so we can say 24 times the reciprocal of this number, which we actually know, 24 divided by 8, and the reciprocal of 8 is 1/8. So we could have done maybe this to find the answer instead of solving it as an equation. Okay. Oops. And then 1 second. So for this one over here, question 5, it says the floor plan of a restaurant. So let me draw the floor plan. This is in your notebook, right, in your sketch. You draw the floor plan. And we don't have the dimensions, but we know the area is 16 inches squared. 16, is that what it says? 16 inches squared, yeah. And in real life, Long here says that if we were to actually go to the restaurant and measure it, it would be 700 feet square. Is it correct? So that's what the question is asking. So let me write this up here. Our problem is that the plan area, the floor area in our notebook, floor area is 60 inches squared. And we want to change that to feet squared. Yeah? So we have, they're telling us that each inch, right, is 12 feet in real life. Okay. So we're going to change the inches here. We're going to say 16 times, actually the inches. So because area is not just length times width, okay, they both get multiplied by 12. Oh, shoot. Okay, let's talk about this problem here. Um, there's a floor plan of a restaurant, and it's 60 inches squared. And Huang actually went to the restaurant and he measured it, right? And he did it in feet. And he says that the drawing in his notebook, 60 inches square, um, in real life is actually 750 square. Let's think about what that means. Okay. How can I explain this the easiest way? Well, let's imagine that this is 1 inch on each side. So this is 1 inch, and this is 1 inch, right? If I asked you to find the area here. You would say, well, that's easy. It's length times width, which is 1 times 1, and the area is just 1 inch squared. So the kitchen floor has 60 of these. Okay, 60 of these. 60 of, in whatever layout it is, but if you were to collect all of these 60 and put them together, count them and put them together, you would have 60 of them. Okay, now what that means that every inch squared in real life is represented, because we have a scale, and it says that every inch is 12 feet, right? So that 1 inch squared in real life is 12 feet. And if you multiply 12 times 12, we get 144 feet squared, right? So, but how many of these little squares are in your notebook? In your notebook design, when you drew the layout of the kitchen, there were 60 of these. 1, 2, 3, 4, 5, 6, etc. 7, 8, 9, 10, 11, 12. There were 60, and that's why you got the area of 60. So 60 of those times 144, right? Because there's 60 in terms of feet, right? This, in terms of feet, gets represented by 144 feet squared, because every inch is 12 feet. But how many of these do you have in the restaurant? You have 60 of them. So 60 times 144 is, top of my head, 60 times 144 is 8,640 feet squared. That's a big restaurant. Sorry, I kept saying kitchen, but it's restaurant. Hopefully that makes sense, right? So, and that should have been